Hello again. So this recording covers lecture 15, which is about parts of chapter 14. And when you look at it, it's a lot of the content of this lecture is probably a review of something that we talked about at some point. So we are going to talk about some of these. It's not lecture 18, by the way, it's lecture 15. Must be a typo here. So, if I summarize the networks that we talked about during this course so far, see that we most recently we talked about LANs. So there is the wireless and the wired, two different technologies. Before that, we talked about point-to-point connections, and there are a lot of technologies that are used for just point-to-point. And we talked about specific protocol, which is HDLC. And when you talk, the program is about internet working, so it is the connection among all these networks. So the internet or any other internet work is not all necessarily made of just a single technology. Sometimes there are a mix of multiple technologies. So if you look at all of these and look at the big picture, you'll see that these technologies differ in certain aspects. Uh, this may not be in the summarization of all the aspects here in this slide, but some of them is the addressing schemes. We saw, for example, in HDLC, we use just one address. When we talked about LAN, Ethernet, we used two addresses, source and destination, in the MAC layer. I didn't mention it in the wireless, but actually we use four addresses in the wireless. Right? One address, source and destination for the nodes themselves, and source and destinations for the access points. So addressing scheme differs in each technology, and these are just examples of some of the things that we covered already. Also, maximum packet size. So Ethernet uses something around 1500 bytes. ATM technology, which used to be a very big deal at some point, uses only 53 bytes, and the Ethernet allows the packet to be variable in size, while the ATM doesn't allow variation. It's just always 53 bytes, right? They are different in the way they report status, and we'll talk about the protocol for TCP/IP stack today. Routing methods, how the user get access, timeouts for different mechanisms. We talked about timeouts when we talked about stop and wait protocol, for example, or the ARQ in general. We realize we need to have timeouts. Routing protocols needs timeouts. Almost every protocol has certain timeout mechanism for it. Ways to recover from errors, we talked about that as well. And then we talked about the fact that some technologies are connection oriented and some of them are connectionless, right? So if I look at this particular variations, what is the difference? So we touched on that slightly when we talked about HDLC and maybe some other lectures as well. But in connection oriented, we need to make sure that the other side is ready to receive connections or receive traffic before we send anything. So sort of establishing a virtual circuit, but here the virtual circuit doesn't mean necessarily that we are booking path in all switches, like we talked about virtual circuits in other technologies. So frame relay, for example, is a virtual circuit technology where before any two nodes can connect, we have to tell all the intermediate switches that we need to book this virtual circuit. But even if we don't use this mechanism, still TCP, for example, is sort of connection oriented. It is a connection oriented service where before node can talk to another node, they have to establish a connection first by sending a signal that says, I want to establish a connection, and the other side replies and say, okay, you can, right? Or you can't. So that establishes a connection between the two before even packets are sent. So that's one requirement of a connection-oriented service. So there are intermediate systems between any two nodes, right? So the intermediate systems can appear as data terminal equipment to each network. So what that means is, if I look at a network, so here's a node and there are multiple devices in the middle, and another node, right? So these could be routers, for example, in the middle. Here is the nodes. So if you look at, so if I have a connection-oriented service between A and B, because that we talked about transparency of layers and each layer talk to each other, so we can have a connection-oriented communication between A and B at specific layer. Below that, each two devices will consider the network as point to point. So A with router 1 are two nodes communicating and sending frames to each other. So between these two, there are termination points, and the traffic will go from one end to the other, right? And then the traffic will be forwarded. And so for each one of these segments, the two ends of the segment will deal as endpoints to each, relative to each other, right? So sometimes this connection oriented happens at each segment of the segments that we talked about. Sometimes happens only at upper layers, right? So the example that we'll talk about is the TCP/IP. The IP protocol itself is not a connection-oriented protocol, but the TCP is a connection-oriented. So communication between one end to another, between in one segment, is not connection-oriented. So the router and the node, or router and router here, they don't need to establish connection among themselves before they send anything. But node A and node B do, through different layers of the protocol. So any logical connection between two endpoints happen by making these smaller point-to-point connections or concatenation of logical connections across the network, right? To get a packet from one end to another, we have to jump across multiple hops, right? And that will build our path, right? So some of the communication protocols that we talked about offer connection-oriented service at different levels. So FDDI LAN or the 822, they're not connection-oriented, but X25, for example, can be used on top of either one of them to provide the equivalent of a virtual circuit. So now I mentioned multiple technologies that are outdated. So the FDDI right now is obsolete technology, and so was X25. But these are early technologies. So the FDDI used to create a ring topology using two paths, and the traffic will go from one node to another, either clockwise or counterclockwise. So it's not really important for our discussion, but we can turn the idea here is turn something that's not connection oriented to something that's connection oriented by putting a layer on top of it, right? And the example is the IP protocol is not connection oriented, but the TCP on top of it is. The connection-less operation, among its main characteristic, is there is no need for the node to inform the other node that, oh, I am trying to send you something. It just sends the packet, right? So it sends the packet and hopes for the best. Hopes that, okay, so the network will deliver the packet to the destination. And also there is no mechanism of making sure that the packet has arrived correctly. So there is no acknowledgement. Right? One of the examples is, as I said, is the IP protocol. Right? We looked at some of the HDLC, for example, that's mentioned here. If you go back to the slides, you will notice that HDLC can be used also as connection-oriented protocol, because we have the unnumbered frame, if you remember, were used to establish a connection before we send anything. All right, so if I compare the two quickly, so the advantage of the connection-less service is it's flexible. There is no establishing of virtual circuit or any type of circuit beforehand. I can just send packets and that's it. Because it doesn't have to follow specific paths, then the network can manage to send the packet in any available path, right? Whatever is available, which makes it in some sense robust, because if something fails in one area of the network, another area of the network will take care of the delivery. As long as there is available path between the source and destination, we will get the packet received. There is no overhead of establishing a connection, right? Disadvantage, it's unreliable because the packet may be delivered or not. There is no feedback mechanism. While if I compare that to the connection-oriented service, there is always an acknowledgement, right? You send a packet or series of packets if you have a window, and you receive acknowledgement. So you always know that the packet is delivered. If it's not delivered or delivered with errors, you retransmit again, right? Because packets in the connection-less can take different routes, they may arrive out of order. By the way, TCP also, because it relies on IP, so TCP also, it's possible for the packets to arrive out of order, but the TCP will order them for you, right? The TCP will take care of ordering the packets. Any issue with reliability, so let's say we're using a connection less protocol to send temperature, right? So that's a perfect service for sending a temperature from a temperature sensor to a station. So because why is it good? Because, well, the temperature, we send it, let's say every minute we send the temperature. And let's say the packet is lost or did not arrive correctly. So that's okay, because in another minute we will be sending another packet with another temperature reading. So we don't really need to establish a connection. Actually, establishing a connection is maybe bad, because the sensor will continuously send traffic to the server, right, that's collecting information. So if I want to establish a connection, means that I have either to establish a connection and tear it down with every measurement, which means a lot of overhead, or establish a connection once and make it last forever, which is another bad thing, because connections use resources. So an ideal service is using a connection less to send uh, temperature readings. And we can rely on the application layer on the top to make sure that the reliability is maintained. How? Or any other layer, not necessarily application, but any other higher layer. So by, for example, saying that the temperature reading was received at 10 a.m., right? So the reader will know that, oh, now it's 11 a.m., so this must be an old reading, or maybe I should uh, wait for a new one. So this is just an example of relying probably on a human to maintain the reliability, but we can use um, any other upper layer mechanism to make sure that the network or the service is reliable, right? So we can always build reliable service on top of unreliable service. Uh, you have seen this picture before, and it gives you a general idea about how internetworks works, and especially the IP protocol. So if you look at one end here, end A, you see that there is the TCP, the IP layer, and then if we are using a technology like Ethernet, we have LLC and MAC, and then there is a physical link. By the way, the Ethernet defines all these three layers. So it defines the physical, the MAC, and the LLC. Right? We saw examples like when we talk about 10 base T, so the T is for twisted pair, so that specifies the physical properties or the physical layer as well, right? So the router here has to accommodate both the Ethernet on one side and the frame relay technology on the other side. So it has a physical port that implements the physical layer of Ethernet, and it has another port that implements the physical properties of the frame relay. It has the MAC and LLC, a common IP, and then the LAFP, which is the data link for the frame relay. So a packet comes from the application to the TCP, to the IP, to the LLC MAC physical, is sent all the way. It has to go up, up, up until the IP. So the IP is the only common thing between the two networks. So the network has, the frames have to go all the way up to the IP. Now they are sent through the data link of the frame relay and the physical and so on. So you will see here that we started with data, we added the header for the TCP, we added the header for the IP, and then we passed it down, and we adding headers and the checksum at the end here. And then when we pass it between T8 and T9, we have the header of the frame relay and the trailer, and then it goes back to the Ethernet again. So you will see here that what was common is the IP. The IP part didn't change, right? So the IP frame and what's inside it, which is TCP and data, it did not change throughout this. All right, so with the connectionless service, actually even with the connection-oriented server, we have issues, not issues, but we have things that we deal with. Routing, the lifetime of the packet itself, fragmentation and reassembly, error control, and flow control. So let's look at some of them. We looked at others before, so the flow control and the error control, we looked at it before. We are going to talk about routing later. Let's talk about the fragmentation here. So we talked about, there are two, and this is important to understand, there are two concepts here that you have to separate them, right? So the first concept is we talked about before when we say we have data at the application layer, and this has to go down through the layers below it. So the application may decide that, oh, I have a big file, I'm going to chop it into smaller pieces, and then each piece, piece 1, piece 2, piece 3, will go to the TCP layer where we add a header, and then we pass it through the IP. So this part goes here, and we add a header for the IP, and then we add a header for the LLC, and so on, right? So this part, taking a large data and dividing it into smaller pieces to go through the all of these layers, is probably something that happens not probably, it's something that happens before we send any traffic. So the packet will, by the end here, the packet will be sent with payload here, and it has the MAC header and the MAC trailer, right? And it will be sent across the network. Now we saw this example before when we said we have a lot of data and we are sending it through multiple frames, and we number the frames, frame 0, frame 1, frame 2, and the reason behind that is at the other end here we have to take these frames and we assemble them, so at the end we will have our original data arrive correctly on the other side with the right order, right? Now, how is that different from this fragmentation that happens actually not at the ends. This part of the, I call it segmentations, just to make a difference. So this segmentation of the data and packetizing it and put it in packets happen at the end, happen at the node, the end node, before sending anything, before sending packets. But the fragmentation that we are talking about here happens inside the network itself. So we have this node, and it needs to connect to a router here, and then another router, then another node. So what happens if this part here accepts packets that has a size maximum of 1500 bytes, right? Which common for the Ethernet. But this network here does not allow more than 500 bytes to pass, because it's either different technology or because the administrator decided to set it up so that it doesn't take more than 500 packet frames at a time. So how do we handle this situation? The node here does not know about this network, so it sends the traffic based on the specification of this network, which is, okay, I'm gonna segment my data to pass in frames that have 1500 bytes size, right? And I'm gonna send it. But this router here sees the 1500 byte and say, well, I cannot send this frame as is through this segment, this middle segment here. I have to break it down so that's a different issue, right? So we have to have now a mechanism to divide the packet that we received, or the frame that we received, and make it fit the middle segment that um, doesn't accept more than 500 bytes. So to do that, now remember that I'll use different colors here to illustrate. So the frame coming from A to R1 has the header and the trailer, right? And inside it, we have, this is the MAC header, and this is the MAC trailer. Inside it, we have the LLC, and then inside that, we have the IP. So now I'm gonna use a different color. So we have IP and TCP and the data itself. And this is really what we care about, right? So this part is, it changes every time we send a segment, we send a frame from A to from one node to another across the same segment. What happened? The router will receive the frame, and because it wants to send it to another segment, so it will change the header, the LLC, and the T with its own header, its own LLC, and its own trailer here. As we saw in this example here, this part remains the same, the middle part, but the headers for the data link headers and the physical, or actually there is no physical header, but the data link headers change every time I send it across segment. So we are keeping this part. This is what we need to deliver to the end. Okay, so what if we go back to our problem? What if this size is too big? We cannot send it. So how can we divide this in a way that we can make the frame fit. So again, we have this green part that consists of the IP header, right? And then let's use this TCP header and then the data itself. Now R1, before sending it to R2, needs to change the other headers, the MAC and the LLC header. All right, so I need to put the MAC header here and the LLC header here and the trailer here, and I want to put something in between so that the whole thing is 500 bytes instead of 1500 bytes. So how do I do that? All right, so I can chop this into multiple pieces. I don't know, 2, 3, 4. It depends on how much I can fit. So let's say we divide it into 4 pieces. So the 4 pieces here, we can take this part, which is the IP header, and some of the TCP data and send it. So we'll call this part 1, 2, 3, 4 here. And then then there will be another packet, another frame, I should call it. I told you before that I mix the term frame and packet all the time. It's just makes more sense to me to call everything packets instead of dividing it. So now we have no green part, no IP header. We have the second part of the original packet, and then we repeat the same thing 2 more times, and we'll put the third part and the fourth part here. Right? So that's happen at R1. So R1 take care of this fragmentation here, so that the packets will fit the segment. All right, so I said before that some of this is a repetition of what we talked about. So we talked about fragmentation before, or segmentation before. And so the reason is we didn't split the IP. Why didn't we copy the IP header multiple times or copy the TCP header multiple times? Why didn't we just repeat these multiple times? Actually, because we don't need actually, I have to be careful here. We don't need to repeat all the headers. We need to repeat some of the headers. So here, each one of these frames will travel separately from R1 to R2, or maybe there are more networks here. Each one of them, from this point on, they have to travel on their own. So if they want to travel on their own and reach B, I have to include information here that allow them to reach B. So which information I need to replicate and which information I don't need to replicate? So I need to replicate the IP header, definitely. Why? Because the IP header is the part that allows the packet to arrive to the destination. It has the source and destination addresses. So I need to replicate this part multiple times. As I said before, now I divided this into 4 in purpose, because otherwise 3 segments would be enough. But I know that the IP header has to be replicated, so 1500 divided by 3 will be 500, but that's not enough. I need more. All right, so but the red part does not need to be, the TCP does not need to be divided multiple times. So we have a small chunk here, or a big chunk of the TCP header goes to 1, and then another chunk goes here, and another chunk goes here, and a fourth one goes here, right? The TCP header does not participate in the routing, so we don't need to replicate it. So if you go to this slide here, you will see that when we look at the fragmentation, we copied the IP header for each fragment, but we didn't really copy the TCP header. We just divided the whatever the payload of the IP header into smaller segments and sent them. Okay, is that enough? Well, not really. We still have to have something else. So when I talked about, you have to be careful about the idea of taking the data and segmenting it and sending it, and the difference between that and the fragmentation that happens at R1 is that here, when we send these segments, each one of these frames that are sent, it has a frame number, right? Whatever the technology is, whether it's TCP or HDLC, each one of these will have a frame number, right? Frame number 1, frame number 2, frame number 3, and so on. So the destination will know how to reorder them, even if they arrive out of order, right? And all the windows and the ARQ work by monitoring the frame numbers. Here, if I copy the IP header, just simply copy it, this means that I don't know the relationship between these fragments. What if at later point in the network they arrive out of order? So how does the destination know how to order? These are originally one fragment, one packet, right? They were one packet, and they were fragmented into 4. So the destination knows how to order the packets, but how does it know how to order the fragments of the packet? So we need to include more information in the IP header to refer to the fragments. So we need to have additional information in the IP header itself that provides us with the location of the segment relative to the entire packet. So in another word, let's say each one of these is 200 bytes length, right? So the first IP header will include an offset equals 0. This means that, well, these bytes that are arriving, they should be put at the beginning here. And the second fragment will have an offset of 200. So these numbers are hypothetical, so don't fixate on them. So the second So when I see offset of 200 means that I have, if they arrive out of order, it means that when I look at my fragment here, I should leave 200 bytes empty, and I should fill this fragment from starting from byte 200 and onward. This will have a fragment of, or offset of 400, and finally it will have an offset of 600. So now when the destination receive the fragments, even if they are out of order, this offset number will let the destination know how to put them properly, right? So who's responsible for putting everything back to the way it was? Is it another router? Is it R2 or the destination? Well, as a matter of fact, once the packets are fragmented, the only entity that can put them back is the destination, right? Nobody else. Why? Well, consider this scenario where we have a network that looks like this. Right? So here we have this segment that has 500 byte limit, and then we have this network. So if R2 will start putting it, or first of all, for R2 to put them together, it has to do more processing. We don't want to do that. A second, they may be fragmented again, so we'll start putting things back and forth. So in terms of efficiency and for other reasons, we just let the fragments go until they reach the destination, and the destination will put them back. I think by now we talked about IP so much that I don't know what else we talk about, except that we probably need to look at the actual frame of the IP protocol, and we have an entire course talk about TCP and IP. So there is plenty of information to discuss yet, but in this case, we're just going to look at the header itself. So the main thing in the header we talked about before is the source and destination addresses. We just talked about the fragment offset, so that's where we put it here. And remember the header checksum that we talked about when we talked about error detection? Or that's put here. We have the version number, so it's either version 4 or version 6. We have something here for, we call it differentiated services. That gives priorities to the packets. I think we're going to talk about this at some point in the future. Here, this indicates the total length of the IP packet. The protocol indicates whether we have a TCP or UDP in the payload or any other protocol, so we put the protocol number here. And then the time to live, this is a number that to prevent a packet from going in the network forever and ever and ever and doing loop, what we do is we put a number here. So we have 8 bytes, a byte here, so we can put up to 255, right? And what happens is every time the packet arrives to a router, the router will decrement this number, right? So it will take the TTL and subtract 1 from it. As long as the TTL is greater than 0, the router will say, okay, we'll just forward it. Once the TTL, if I subtract 1 minus 1, I get 0, so the router will say, I cannot forward this packet anymore. It expired, right? And I'll drop it. So that will prevent the packets from going in the network forever for some reason or the other. It is possible actually to create loops in the network by misconfiguring routing, so the packet may go around and around. So this is a way to prevent that from happening. And then the IP header has options we didn't discuss yet, but there's options that we can add. So we talked about the IP header being 20 octets or 20 bytes, but actually if we add some of the options, it extends further. So the padding is meant to make the packet size multiple of 16 bits, I think, or multiple of 2 octets. Um, so we may need to add empty bytes here to just make it um, um, equal to multiples of 60 of 2 octets or 4 octets. We'll see here each one of so this is 1 byte, 1 octet, this is another octet, and these are 2, and the source and the destination addresses, as you probably know by now, it's 32 bits, so there are 4 octets each, right? IP is one protocol that works on layer 3. We have another very common protocol called the Internet Control Message Protocol, the ICMP. And the ICMP sits somewhere between not exactly layer 3 but not layer 4 either. So we have the physical, we have the data link, we have the IP, and we have the TCP, and we should call it transport, because in the transport layer we have either TCP or UDP, right? And here we have actually the ICMP needs to be encapsulated inside the IP. So the ICMP itself cannot be transmitted alone or directly. It has to be put inside the IP header. So IP and then ICMP. So again, another example of the protocol number here. So protocol, I said TCP or UDP. Actually, there is more. So ICMP could be a protocol that's inside. Right? So what does it do? It provides some management and some feedback. So one example is if the router here decrements the TTL and the TTL becomes 0, so it has to drop the packet and it doesn't forward it anymore. But it just doesn't stay quiet and say, okay, I'm going to drop the packet and not say anything. No, it actually sends an ICMP packet to the source in this case, and tells it, I just dropped your packet because the TTL expired. And this is actually one of the bases for the traceroute utility or traceroute tool if you used it, right? So I'm gonna leave this to another day, but it actually uses the ICMP or this fact to create the tool. Another very common use of ICMP is the ping tool, and the ping tool uses ICMP. The ICMP protocol has multiple messages inside the ICMP itself. One of them is the echo and the echo reply. So if you are sending a packet, ICMP packet, that includes the echo message to a destination, the destination will reply with echo reply. So we could use ICMP here for network management or network monitoring by checking if the destination exists or not. So for troubleshooting the network or for monitoring the network. Right? Another ICMP use is for informing about change of routes in some cases or congestion. So it could be used for multiple purposes. Another protocol that resides in the IP layer is the R protocol or address resolution protocol. So to explain this protocol, we have to go back to something that we talked about multiple times. Right? This picture, for example. Right? So when we send the information from A to B, in this case, what do we need to do? Right? So I'm going to go back and draw the diagram, our stack here. So we have the physical and we have the MAC, LLC, the IP, and then we have the physical and the MAC and LLC and IP, and then the other protocols, of course. Right? So to forward packet from A to B, A needs to know the address of B. Which address is the IP address, right? So to send the data from A to B, we have to form a packet that has, let's say the destination is B and the source is A. I don't, just a side note, sometimes I put the header to the left, sometimes I put the header to the right. I really don't have a convention whether I put the header to the left of the packet or put it to the right of the packet. Here, sometimes you just want to do it this way so that I can say, well, this packet is heading this direction, so this is my destination and this is my source. I don't know. I hope that doesn't confuse you, but I don't have a specific um, rule that says the header always should be to the left or the header should be always to the right. I just draw it any way I feel like. Um, so that's a side note. Now, because we learned before that these, because of this layering mechanism, these two are not aware of what below them, right? So the IP layer on one side and the IP layer on the other side, they communicate with each other as if everything else is transparent, right? That's why we're doing layering. But if A wants to send something to B, it has to first send it to R1 here. And to send it to R1, we need to have the address for R1. So which address in this case? It's the MAC address. So we need to form a frame. So the frame will have the MAC header, which includes R1 as destination and A as source, and then this IP packet inside it. And of course, the frame has a trailer, right, which is the CRC. Right. Okay, so how does A node A needs a MAC address to send something to R1. It cannot just send it using the IP address. The IP address doesn't work on the MAC layer. It works only on the IP layer. So I need to find the MAC address. You could simply wire it or configure it so A knows what the address of R1, right? And by the way, R1 also works on layer 3, right? The routers also work on layer 3, so they have physical and MAC and LLC and IP, right? So, and they have, as we saw earlier, the IP may be common, but it depends on which technology. We may have a different stack here, right? But the IP will be common. So that allows the router to take this black part, which is the IP packet, and encapsulate it in a totally different frame, depends on which technology we're using for the next segment. So A may have, when you configure your node, when you configure your workstation or your laptop or your phone, you need to know the gateway. You need to know anything that happens within the LAN itself. It doesn't need an IP address, although we use it. We'll talk about it later. But to send something outside of your LAN, you have to have the IP address, and you have to have the IP address of the gateway, which is the router 1 in this case. So we use ARP to find the MAC address if we know the IP address. So A wants to send something to B, so it says, okay, first I have to send it to the gateway. I know the IP address of the gateway. How do I know it? Because it has to be configured manually. Or we use a protocol, dynamic protocols like HDLC to find out what. So regardless of the way, we know we have to find it. We have to know it, right? Otherwise, nothing will work. But the MAC address itself, we can find it using the ARP protocol, the address resolution protocol. So how does the ARP, so this is a long story to explain what the ARP protocol is. So the ARP protocol also sets on IP, so it's encapsulated. Actually, no, it's not encapsulated in the IP, but let me double check. It's not encapsulated, it's separate protocol. And it sends the request, and the request will say, if you have IP equal this, please give me your MAC. So that's the ARP request. The ARP reply will come back and say, I am, or my IP. Now I'm just using English, of course, but the terminology is different. So my IP is X, 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 and my MAC is, the MAC address is actually 6, written as 6 segments. Each one of them is 16 bits or 2 octets, and written in hexadecimal usually. So that's MAC. So before A sends something to R1, it sends an ARP request saying, okay, whoever has this IP address, please give me your MAC. So R1 replies with its MAC. So now getting the MAC allows the A to send the frame to R1. R1 wants it to forward it to R2, so it does the same thing. It sends an ARP request saying, whoever has this IP address, please give me your MAC. So it R2 sends the MAC to R1, so R1 creates a new packet and a new frame and send it to R2, and so on until it reaches the destination, right? So why these Macs are not hardwired? Why do we need to do them? Macs, the network or the LAN is supposed to be changing and dynamic all the time, right? And we may take something, we may replace something. So, and the network may have a lot of nodes, so saving them and configuring them manually becomes a hassle. A to talk to B needs to know only two addresses, the final destination address and the next gateway, right? That's the only thing that needs to know, right? If so, it needs to, of course, if it needs to talk about 10 nodes, it has to know the IP addresses of 10 nodes. But we have another mechanism to make that easier, which is the DNS, right? Dynamic. Uh, um, what is DNS? Dynamic Network Service? No, I will check it. But anyway, a lot of acronyms, and sometimes we forget what they mean after a while. But yeah, we use this so that we don't remember all the IP addresses. So when you go to a dalhousie.ca, you don't have to know the IP address of Dalhousie. You just type something that you can remember, which is del.ca, and then another service, which is DNS, will figure out what the IP address is and starts the process. So ARP does this, and probably it's a long explanation for something that's really simple, but I just wanted to um, talk about it here. Now to the last comment that I want to make is it's the ARP requests don't happen with every communication. So there is a cache. So node A, it sends the ARP request, it receives the MAC, it saves it in cache. So next time, so if it needs to send 10 packets in a row, it's not gonna ask for the ARP for the Mac 10 times, right? So it will save it in a cache. The cache expire after, let's say, 30 seconds. So that allows, again, the network to be dynamic. So if I put a new, if the router is replaced, or actually even to save the cache or save memory. If I save all the MAC addresses in the cache or the memory of the node, and there are hundreds of nodes, then I may exhaust my memory, right? But to save the MAC in a cache for 30 seconds and then repeat the process after that, it makes sure that the memory is not exhausted and we have plenty of space. And as I said before, the ARP protocol is not encapsulated inside the IP header. The ARP protocol has its own header, right? So it works directly on top of the data link layer, so it doesn't need ICMP is encapsulated inside IP, but the ARP is its own protocol. It's not encapsulated inside IP, right? So IP version 4 has been around since the beginning of the TCP IP system or set of protocols. And the creators of the standard, they thought 32-bit was enough to cover all our networking needs. It turned out that that was not correct. Due to, well, explosion of people who are using the internet and things, so use the internet and the IP, and also because of early assignment of the IP addresses were not efficient. So they were, let's say a university asked for IP address, so they will give them IP class A address, right? IP class A has 2 to the power of 24, or so like there is an IP, the network part is 8 ports, and the rest is 24 ports, right? So that's a lot of addresses that go to an institution that may not use all of this space. So there is a lot of wasted addresses there. So we ended up with, address space exhaustion. So the IP version 4 space have exhausted for a long time. I think it has been out since 2011, right? So there is no more IP version 4 to be used, to be given. We still, I think, due to some recycling and some, exchanges and all of that, or reclamation, maybe some IP addresses, IP version 4 addresses still being public IP addresses still being used, but essentially we don't have any more IP addresses to give. So people realized that. They came up with short-term solution, which is the network address translation and the private IP addresses. So protocol 1918 says, well, certain IP addresses are not public. You can use them inside your network, but you don't publish them outside. And if you want to communicate to the outside world, we are going to give you 1 or 2 or few public IP addresses. So what do? Inside your own network, you use IP address space like 192.168.2.0, for example. That's inside, do whatever you want with it. And we can use the same IP address for multiple networks. Like you can use 192.168 anywhere you want, like in any network you want without getting permission from anyone. But if you want to communicate with the internet, you have to translate that address to something public, which is limited. Right? So in my case at home here, I'm using network 192.168.2.0/24. But if I want to talk outside, my router will translate that to a public IP address, and that public IP address is obtained from my service provider, right? So everything is translated. So the rest of the world will see my network as one address, while inside my network actually there are plenty of devices, right? So that reduced the need for IP version 4, but still we still need more addresses. So a long story short, well, it's actually a long story made it longer. They came up with a new version, a new IP version called IP version 6. And one of the main features of this is that the IP address itself is 128-bit instead of 32. Right? So it's a huge, and actually, if I think it's enough, I don't know if that's accurate or not, but it's enough to give every sand in the desert its own IP address, and we still have leftover. uh, uh, well, even sometimes they say every atom in the universe or something like that. But anyway, it's take a look at 2 to the power of 128, see what kind of number you get, and that's what I mean, right? So it's a lot of addresses. Uh, the problem with the IP version 6 is that it's not compatible with IP version 4, right? It's not backward compatible. So it has been around for more than 20 years. It has been around since I was a student taking courses like yours. But it's not being used widely yet. It's still being used more than before, so it's the usage is continuous. It's still being it's what I'm trying to say. It's becoming more and more popular now, but there is a slow adaptation of the IP version 6, and the reason is the backward compatibility. So networks and people, they don't want just to throw everything they have and replace it with IP version 6. One of the solutions to avoid this problem is to have dual stack. So dual stack means every router, every node you have, every device you have, it has dual stack. So one stack that uses IP version 4 and another stack that uses IP version 6, right? So TCP will be common, but the IP will have two different. So now each device will speak two languages, right? If you look at your laptop or your phone and check the IP address, check the address, you will see what I mean. So in my case, here I'll have an IP version 6 address here, an IP version 4 both available. So I can communicate with either IP version 6 or IP version 4. It doesn't solve the problem completely because now how do I choose if I want to go to Brightspace, which one I choose, IP version 6 or IP version 4? And my network has to be all the way, not just my network inside, but all the way from here to Dell server. It has to be understanding both. So there are mechanisms to translate IP version 4 embedded in IP version 6 or replace it, or there are many solutions to do intermediate solutions to embed IP or translate IP version 4 address to IP version 6. So that it's a topic by itself, but this is just a brief introduction to IP version 6. And that concludes our lecture, our recording today, and I'll see you in the next recording. Thank you.